Good day, students, and welcome to the second lecture of the LN 2016A Electronics 1 course. I'm your lecturer for today, Mohammed Dango, and lecture 2 will be covering the PN junction and the diode. Kicking things off, we have the PN type semiconductor, followed by PN junction, biased PN diode, diode characteristic curve, and the diode equation. As always, refer to your textbook. This lecture will cover chapter 1, pages 23 to 33. And note that anything said or done in this lecture can and probably will be used as a question to test you in your examination. So first up, students, we've got a bit of a recap. Looking at the intrinsic type semiconductor from lecture 1, you know that this is a semiconductor which has a crystal lattice comprised of only the silicon atoms, in this case, which have 4 valence electrons. We then have the extrinsic N-type semiconductor, which is basically an intrinsic type that has been doped with a pentavalent atom, which is in this case phosphorus, and it's known as a donor ion because it donates a free electron to our crystal lattice, which makes the free electrons the majority charge carriers because there's a lot more of them compared to the holes, and the holes are the minority charge carriers. And finally, we have the p-type extrinsic semiconductor, which is basically an intrinsic semiconductor which has been doped with a trivalent atom, in this case boron, and the trivalent atom basically is known as an acceptor ion because it comes with a hole, and this makes the holes the majority carriers within the p-type semiconductor. There are some free electrons, yes, we can see them, and those are the minority charge carriers within the p-type semiconductor. So now what happens if we take an n-type and a p-type semiconductor and we join them together? Nothing. Nothing happens because that's not how you create a PN-type semiconductor. You actually create a PN-type semiconductor from a single crystal lattice, which starts off as an intrinsic semiconductor, and you basically got to dope one side with trivalent atoms, and you dope the other side with pentavalent electrons. And in doing so, you create the PN-type semiconductor. So here we see on the N-type side, we have majority carriers, which are free electrons, and on the P side, we have the majority carriers, which are our holes. Now we're going to look a bit deeper into this crystal lattice structure. Let's move on to the next slide. So looking a bit deeper into our PN-type crystal lattice, we can see from the P region that we have our trivalent atoms, which are our acceptor ions, which bring in additional holes, which make the holes the majority carriers in the P region. And of course, there are some free electrons, although they are very few compared to the holes, which makes the free electrons the minority charge carrier in the P region. Across our PN junction, over into the N region, we have our pentavalent or donor ions who donate free electrons. That makes the free electrons the majority charge carriers in the N region. And of course, there are some holes present, yes, of course, and the holes, because they are very few compared to the free electrons, they are the minority charge carriers. Now, in this picture, we can still see our covalent bonds, we can still see our silicon atoms, and it's a bit difficult to visualize what's happening at the PN junction. So in the following slide, we're going to just get rid of some of that noise to have a clearer picture to help with our understanding. And here it is. So the PN type lattice simplified. So now again on the P region, we have our positive holes and our negative acceptor ions. On the N region, we have our negative free electrons and our positive donor ions. And right in the center, of course, we have the PN junction. Important slide that we have here for terminology. Students, please keep this in mind moving forward, especially that these are negative acceptor ions and these are positive donor ions in the PN type semiconductor. Now, if we look at what happens at the PN junction, you'd be right to say that there's a high concentration of free electrons in the N region because they are the majority charge carrier, which means there's a low concentration of free electrons in the P region. They're not shown here, but they are there. And because of this concentration gradient, you might remember that there is something called diffusion current. Diffusion current is current that flows due to the presence of a concentration gradient. And we have this concentration gradient between the N region and the P region for free electrons. And we have a concentration gradient between the P region and the N region for our positive holes. And that causes these free electrons to move and recombine with the holes at the PN junction due to this diffusion. Now, when that takes place, what happens is it creates what is called the depletion region. And it is called the depletion region simply because it is depleted of any free charge carriers. All we have are our negative acceptor ions and our positive donor ions. And that, ladies and gentlemen, is our depletion region. And what you know about positive and negative is that there's going to be an attraction between them. But the thing about these ions is that they are immobile. So what they actually do is they set up an electric field within this depletion region. And let's visualize that. Yes, this is what it looks like. So in our depletion region, something known as the barrier potential is set up because of these immobile positive donor ions and immobile negative acceptor ions. And this barrier potential that gets set up, or this electric field, has an actual voltage. For silicon, it's 0.7 volts, and for germanium, that is 0.3 volts. Now, what do we know about an electric field? Well, in the presence of an electric field, we're going to see some flow of charge. And that's exactly what happens at our depletion region, only this time we start looking at our minority carriers. As you know, in the P region, the minority charge carriers are electrons or free electrons, and the minority charge carriers in the N region are our positive holes. So I've illustrated them on this slide, and you can see them coming towards the depletion region. And because of this barrier potential, our minority charge carriers in the P region, which are the free electrons, are going to move over into the N region, and our minority charge carriers from the N region are going to move over into the P region. And you know that a movement of free charge carriers caused by an electric field is a drift current. So in our PN junction or PN semiconductor, we have a drift current in the depletion region caused by the movement of minority carriers due to the barrier potential, which sets up an electric field, EB. Now, students, what we eventually see happening within our unbiased PN junction, unbiased meaning we don't have an external voltage source, is eventually the diffusion current, which is due to majority charge carriers, and the drift current, which is due to minority charge carriers, eventually reaches a dynamic equilibrium. So that is when the diffusion current is equal to the drift current, and this happens just a couple of moments after the instant in time that this PN junction comes into existence. Now, the barrier potential, which we spoke about earlier, which is created between these positive donor ions and negative acceptor ions, we can actually calculate this barrier potential using equation 1.10. Now, the really cool thing here is that this P region, N region, and depletion region in the middle, this, students, is what is known as your diode. And here we can see the circuit symbol for a diode. On this side we have the anode, which is representative of the P region, and on this side we have the cathode, which is representative of the N region. So I think we should put this equation into action with a bit of an exercise. Let's go for it. So, calculate the barrier potential for gallium arsenide PN junction at a temperature of 300 Kelvin, acceptor ion concentration of 10 to the 6, donor ion concentration of 10 to the 17. Repeat part A for germanium PN junction, the same doping concentrations. Students, it's a very simple plug and play. So we have our barrier potential for gallium arsenide, our thermal voltage, which you know is 0,026 volts. This is something that will be given to you. And the intrinsic carrier concentration, do you remember this from the first lecture? Yes, we calculated this in the first lecture. I think it was our very first exercise. The intrinsic carrier concentration for gallium arsenide, we plug that into the equation and we solve for our barrier potential, 123 volts. What a nice way to look at it. And then for germanium, exact same thing. We got our intrinsic carrier concentration of germanium from our first exercise in lecture 1 and our thermal voltage of 0,026 volts. That's a standard thing that's given. We get a barrier potential of 0,374 volts. Excellent. So moving on, we can now look at what is known as the biased PN junction. Now previously, our PN junction did not have an external battery connected onto it. But now, when we do connect a battery to our PN junction, it is what is called a biased PN junction. And because a battery has both a positive and negative terminal, this means there's two ways that we can connect our battery to our diode or to our PN junction. The first being the reversed biased condition, where the negative terminal of the battery goes to the P region, or as you'll remember, the anode of our diode, and the positive terminal of the battery goes to the N region, or the cathode of our diode. And for the forward biased condition, our battery's positive terminal is connected to the P region, or the anode of our diode, and the negative terminal of the battery, yes, you guessed it, is connected to the N region, or the cathode of our diode. Now what happens when we set up this biased PN junction? Let's look at forward biased condition first. So students, for the forward biased condition, we are now biasing this diode with a voltage VD from this battery. And this voltage VD is greater than 0, but it's very much less than our barrier potential voltage. And what this does is this voltage VD then sets up a very weak electric field within our depletion region, as it's demarcated by ED. And you can see that these very thin gray lines are this weak electric field ED, and EB is the electric field that is created by our barrier potential. Now we do see that there is some current that flows, although it is very little current. In fact, it's negligible when you are operating in this region, and this is known as ID, which is the diode current. But now what happens when we start to turn up VD and start increasing the strength of this electric field ED, which is in the opposite direction to our barrier potential electric field? Well, looking at this slide, our battery voltage VD is much greater than 0, but it's still less than our barrier potential voltage. So what we see happen is the width of our depletion region has decreased, and ED has gotten slightly stronger, and our EB electric field has gotten slightly weaker. So because the electric fields are in opposite directions, they compete with each other and they are subtractive. So now what happens when we increase VD even further? Well, of course we can expect this electric field caused by VD to get stronger. So here we can see that we've increased our bias voltage VD much greater than our barrier potential voltage VBI, and that means the electric field ED, which is created by our battery, overpowers and completely eliminates the electric field created by the barrier potential voltage. Now, as we know, in the presence of an electric field, there's going to be a flow of charge. So our free electrons in the N region, which are the majority charge carriers, are going to start flowing in the opposite direction to the electric field ED and into the P region, and in the opposite direction of the diode current and into the positive terminal of the battery. On the other end, we have our positive majority charge carriers, which are holes in the P region. They will flow in the same direction as this electric field ED and in the same direction as conventional current into the negative terminal of the battery. And that, students, is what happens in the forward biasing condition of our diode. And let's take a look at what this looks like if we were to go ahead and plot it. And here we are, students, where we're going to actually plot what's going on in our depletion region when we forward biasing our diode. We showed you three cases. In the first case, the bias voltage VD was greater than 0 but much less than the barrier potential voltage. That's this region over here. As you know, not much current's going to flow. But as we increase our bias voltage greater than 0 but still less than our barrier potential voltage, that's this region over here. Yes, we still have some diode current flowing, but not very much. But the real magic happens once we increase our bias voltage greater than our barrier potential voltage, and we completely eliminate the barrier potential voltage's electric field, which allows for current to start flowing. And that is at this point over here, and it's called the diode on point. And because our diode switches on at this point past our barrier potential voltage, we can refer to our barrier potential voltage moving forward as our diode on voltage, or VD on. Now for silicon, we know that our on voltage is 0.7 volts, for germanium 0.3 volts, and for gallium arsenide 2.8 volts. And that, students, that covers our forward biasing of our diode. This is an important graph for you to remember or plot, because in your lab 1 you are going to be doing an experiment, and part of that experiment is to forward bias your diode, take certain measurements, and then plot this forward biasing curve. Alright, so now moving on, let's go and have a look at what happens in the reverse biasing case. So in the reverse bias condition, as we've seen, we swap the battery around and we take the positive terminal of the battery and connect it to the diode's N region, or cathode. And we take the negative terminal of our battery and we connect it to the diode's P region, or anode. Now similarly, as was the case with the forward bias condition, this battery is going to set up an electric field inside the depletion region. Now, instead of being in the opposite direction of the barrier potential's electric field, it's now in the same direction. So it's obvious that these two electric fields are going to sum and create a much stronger electric field. And what happens in this case is, because we have a much stronger electric field in our depletion region, we start to see some minority carriers from the P region, which are free electrons, illustrated here, and some minority carriers from the N region, which are holes, illustrated here, start to flow through the depletion region. So the minority charge carriers are now starting to flow. Now this flow of charge carriers is very minimal, and that's why we have a small current that we see flowing, known as the saturation current. So when we reverse bias our diode, if we have a applied voltage that is less than 0 but is still greater than something known as the breakdown voltage, which we will get to, we see a flow of minority charge carriers from the P region and from the N region within our depletion region. So now what happens if we were to decrease this applied voltage VD and get it closer to our breakdown voltage and even further or less than 0 volts? Well, here you have it. So again, you can see this electric field, which was set up by our barrier potential, now gets even stronger because it has the additional power of the electric field created by this external biasing, and it increases the width of our depletion region. Now again, because we have a stronger electric field, we're still going to get electrons, which are minority charge carriers from the p region, moving across, and holes, which are minority charge carriers from the n region, moving across. And this movement of charge carriers sets up this very, very minimal saturation current. But now let's take it a step further. What if we were to decrease this reverse biased voltage even further past the breakdown voltage? What do you think is going to happen, students? Let's take a look. So our voltage has now been decreased to a point where it is less than the breakdown voltage, and a whole lot of crazy stuff starts happening here in the depletion region. Look at this electric field, which is the barrier potential electric field summed with the electric field created by this external biasing. It is incredibly strong. So strong that it starts to attract minority carriers from the p region, which are these free electrons. Here they all are, and it gets them moving across the depletion region and into the positive terminal of the battery. And it gets the holes, which are the minority charge carriers from the n region, to move across the depletion region and into the negative terminal of the battery. And what we see is massive amounts of current starting to flow. But now, why does this happen? Why does this condition known as breakdown happen? And specifically, this type of breakdown that we're looking at here is known as avalanche breakdown. Well, the reason for this is because this electric field that is now created, which is the sum of the barrier potential electric field and the externally biased electric field, is so strong that it imparts kinetic energy to these free electron minority charge carriers. So much kinetic energy that they start bouncing around and hitting into the covalent bonds between our intrinsic charge carriers or our silicon atoms, and they start to break the covalent bonds of these silicon atoms. Now you're looking at this picture and thinking, but sir, this is a simplified picture. We can't even see the silicon atoms. So let's move on to another picture where I hope to try and illustrate this avalanche breakdown effect a bit better for you guys to understand. So here, students, I'm going to attempt to explain avalanche breakdown to you. Now remember what I said is that the free electrons are now in an extremely strong electric field within the depletion region, and this electric field is going to put a lot of kinetic energy into these free electrons. So here at the starting point is we have a free electron, and you can assume that its whole pair is somewhere here at the back. We haven't illustrated it, but this free electron is sitting in that extremely powerful electric field. It gets a ton of kinetic energy and it flies into this bond between two silicon atoms. Yes, the silicon atoms are still present in our crystal lattice. And when it bangs into this silicon atom, it breaks this covalent bond. We move over onto the second picture or illustration, and now from one free electron we have two free electrons, and each of these free electrons has their whole pair. Here we have illustrated the whole pair for the free electron that was broken off, and the free electron that started this mess, well, his whole pair is somewhere at the back here. Now both these free electrons are still within this incredibly strong electric field, so both of these free electrons get a ton of kinetic energy, and they start smashing into other covalent bonds, as you see here. So now from 2 electrons, we then end up having 4 electrons. And this process is going to repeat itself. So we started off with 1 free electron whole pair, we moved into 2 free electron whole pairs, we went to 4 electron whole pairs, and so on. And that is why it's called the diode avalanche breakdown. Now I know this might be a bit of a difficult concept to wrap your head around. Please take some notes, come to the Thursday lecture enrichment session, and let's have a chat about it if you still don't understand diode avalanche breakdown. And just as a reminder, here we have the diode avalanche breakdown initial image. When our voltage applied is much less than the breakdown voltage, we see an incredibly strong electric field, which is the barrier potential electric field plus the external biasing electric field. This then causes a flow of minority charge carriers from the P region, which are free electrons, and a flow of minority charge carriers from the N region, which are holes. Now, if we were to, in a similar fashion, plot what the hell is going on in reverse saturation and in the breakdown region, as we did with the forward biasing, this is what our diode curve starts to look like in the reverse bias and breakdown region. So as you'd remember, as we just less than 0 but much greater than our breakdown voltage, so that's this region over here, you see that we have very little current flowing, which is our saturation current. And as we decrease the applied voltage to a point where it starts getting closer to the breakdown voltage and further away from 0, we start to get into this region where we are approaching breakdown voltage. And finally, once we go less than the breakdown voltage at this point over here, massive amounts of saturation current start flowing, and we are now operating the diode in the breakdown region. Now I've thrown in a sneaky little equation over here, equation 1.11, and equation 1.11 is used to calculate the junction capacitance, because when we are looking at our depletion region and we have our positive donor ions and our negative acceptor ions which set up this electric field, you might think to yourself, that looks awfully like a capacitor. And you'd be correct, because it is a capacitor. And we can calculate that capacitance using this equation for junction capacitance. So let's see that in action. A silicon PN junction at a temperature of 300 Kelvin is doped with a Na of 10 to the 16 and an Nd, which is donor concentration, of 10 to the 17. The junction capacitance is given. Cj is 0.8 picofarads. When a reverse bias voltage of 5 volts is applied, find the zero bias junction capacitance. Now, the zero bias junction capacitance is basically the capacitance in the depletion region when we have no external biasing on the diode. So, looking at this, we can first calculate the diode on voltage for silicon using this equation that we had gotten previously in the lecture. Vt, the thermal voltage, you know it's 0.026 volts, and the on voltage for silicon, as expected, 0.757 volts. Now that we have that, we look at our junction capacitance equation. We do some hammering about to make the junction capacitance in the zero bias condition the subject of the formula. And then it's a simple plug and play so that we can calculate 2.21 picofarads as our zero bias junction capacitance, or Cj naught. Okay, students, this is an extremely important slide for you. This is our diode characteristic curve, and the one that I'm illustrating here is for silicon. Now, why is this an important curve? Well, because this is laboratory 1. As I mentioned, you're going to be doing an exercise or a practical in the lab, and you're going to then take measurements across a diode when you're operating it in forward bias condition, reverse bias condition, and breakdown. And you're going to take measurements across this diode and see what the saturation current is, what the forward bias current is, where the D on occurs, and where the breakdown occurs. So as you can see from this graph, we have our breakdown voltage, we have our on voltage, our forward bias region, reverse bias region, and breakdown region. Also important to note is the scale of these axes. Firstly, the current scale moving up. We have milliamperes. That's because our forward biasing current is in milliamperes. It's quite high compared to our saturation current, and that's why our saturation current is in microamperes. because very little saturation current actually flows in the reverse biasing condition. And that's why you see here I've illustrated it or noted it further. ID is negative IS, which is saturation current in microamperes. Also, looking at the voltage scale, we know that our on voltage for silicon, it is at about 0.7 volts. That's here. But the breakdown voltage for a silicon diode is quite high, approximately 50 volts. Some of them can go up to 1000 volts. But for this one, we've got it at around 50 volts. And that's why you see our breakdown voltage is over here. And in this diode, we have avalanche breakdown taking place. And the two circuits that we have illustrated here, this shows us our reverse bias connection, and this shows us our forward bias connection. Now, the breakdown that we've covered so far was avalanche breakdown, which take place in a diode that is very low doped. So our breakdown voltage could be up to 1000, maybe even 30 volts on the minimum side. But then we have another case of breakdown known as the Zener breakdown. Now this will be covered in more detail when I talk to you guys about Zener diodes. That's coming in a later lecture. But what you need to know now is that these diodes are very highly doped, which gives them a breakdown voltage of approximately 5 volts or so. Next, we look at temperature effects on our diode characteristic curve. This is specifically for avalanche breakdown, not Zener breakdown diodes. As our temperature increases, so from T0, we increase to T1, we increase to T2, we see that our saturation current starts getting a lot higher. So at T0, we're at a low temperature, we increase the temperature, saturation current goes up, we increase the temperature, saturation current goes up. With saturation current going up, obviously our breakdown voltage is also going to go up. And on the other side, in our forward biasing condition, as temperature goes up, our VD on, or our diode on voltage, that starts to decrease. That's why you can see they are inversely proportional in this case. Important to take note of temperature effects when you're building circuits with diodes. You don't want your diode to start heating up, because it's really going to mess up its operation, guys. And I have seen this, and it's not a nice thing to have. And finally, students, the most important slide of this entire lecture, the diode equation. The theoretical relationship between the voltage and current in the PN junction or diode is given by equation 1.12. Take note of this equation, because in the next lecture we're going to be using it to actually solve diode circuits. But before we do that, let's do a quick exercise. A silicon PN junction at a temperature of 300 Kelvin has a reverse saturation current of 2 times 10 to the minus 14 amps. Determine the required forward bias voltage to produce a current of 50 microamperes, and secondly, for a current of 1 milliampere. So this is a very simple exercise to get you guys familiar with the diode equation. All we got to do is rearrange the equation so that we can make the diode voltage the subject, and then it's a matter of plug and play to calculate our diode voltage to achieve the different diode currents that you have here. Don't worry too much about this exercise. There's going to be a lot more complicated stuff coming up in the next lecture, where we look at different ways to actually go about solving this diode equation and diode circuits. And that, students, is the end of lecture 2. Thank you very much for participating and listening if you are here. So students, as a quick recap, we started off looking at the PN type semiconductor. Remember, it is not a p-type and an n-type semiconductor that is then joined. It is a single intrinsic semiconductor which has one side doped with p-type trivalent and the other side doped with n-type pentavalent atoms. And that creates the PN junction in the middle. And you'll remember that at this PN junction, we have a diffusion current that flows due to concentration gradients, and this then sets up the depletion region in the PN junction. And then in the depletion region, we have positive donor ions and negative acceptor ions, which are immobile. So they set up the barrier potential, which has an electric field within the depletion region. And of course, this electric field within the depletion region causes a drift current to start flowing, where we see minority carriers from the P and N side start to move across the depletion region. And eventually, this drift current and diffusion current become equal to each other, and the PN junction has reached what we call dynamic equilibrium. We saw an equation that can be used to calculate the barrier potential voltage, which we later knew from the forward biased PN diode is the diode on voltage. And we looked at the reverse biased PN diode and saw that when we reverse bias it, there is a very small saturation current that flows, but as we increase or rather decrease that reverse bias voltage past the breakdown voltage, a very strong electric field gets set up in the depletion region, which imparts a lot of kinetic energy to free electrons, who then start breaking covalent bonds between the silicon atoms, and that creates the avalanche effect. And from our biased PN diodes, we were able to plot our diode characteristic curve, a very important curve because that is your guys' lab 1. And finally, students, we looked at the diode equation. We did a very, very simple exercise just to give you guys a taste of it, and more complex stuff coming up in lecture 3. Thank you to those that did participate and have watched this video. I do appreciate any comments or feedback that you might have. Please bring your notes to the Thursday lecture enrichment session. And of course, refer to your chapter 1, pages 23 to 33 in your guys' prescribed textbook. I appreciate your time. Thank you very much.